Hey there and welcome. So glad you're joining us for this explainer and exam review. You know, as a professional engineer, I spend a lot of my time obsessing over how massive things are built. Think huge bridges or towering skyscrapers. But today, we're zooming way in. We are tackling the microscopic building blocks of solid-state physics. We're going to dive straight into the hidden geometric world that literally holds our entire physical reality together. Let's get right to it. All right, here's our game plan for today's review. First, the basics of crystal lattices, then the 7 crystal systems, inside the cubic system, mapping with Miller indices, X-ray diffraction, and Bragg, and finally, a power review for your exam. Let's hit it. Section 1. The basics of crystal lattices. We are starting right at the foundation of material structure. So, if you want to understand a huge, complex system, you really have to look at its smallest repeating part, right? Think of a unit cell exactly like, well, a single brick in a massive wall, or maybe like one repeating square in a piece of 3D wallpaper. If you can figure out the properties of just this one tiny brick, you can actually predict the structural integrity of the entire building. Now, how do we actually measure that microscopic brick? Well, just like defining the dimensions of a room in your house, we define this unit cell using its lattice parameters. We're looking at 3 edge lengths, we call those A, B, and C, and the 3 angles between them, alpha, beta, and gamma. It's wild, but by just slightly tweaking these lengths and angles, nature can build completely different materials.
Moving right along to Section 2, the 7 crystal systems. Because, as it turns out, nature doesn't just use one shape of brick.
Okay, pause here, because this is your ultimate cheat sheet for the exam. This lays out the exact mathematical rules for how edges and angles have to align to form specific structures. Take a perfect cubic system, for example. Edges A, B, and C are all exactly equal, and every single angle is a crisp, perfect 90 degrees. But if you stretch one side or maybe tilt an angle, suddenly you're in the tetragonal or monoclinic system. It's honestly a lot like squishing or stretching a cardboard moving box. And way back in the mid-1800s, a physicist named Auguste Brevet proved something super cool. He showed that when you arrange atoms in space within those 7 basic box shapes, mathematically, there are only 14 unique ways to pull it off. We call these the 14 Brevet lattices. Think of them as the 14 master blueprints for basically all solid materials in existence.
Section 3. Inside the cubic system. Let's zoom in on the absolute most common system you'll be tested on.
Check out these 2 critical variations. First, we have the simple cubic. It's got an atom sitting precisely at each of the 8 corners of our box. But then we also have the body-centered cubic, or BCC for short. Notice how it takes that exact same simple cubic box, but boom, drops one solid atom right in the dead center of the room. That one slight change, it completely alters how strong and flexible a metal is going to be. Now, what's the deal with this 52% number? Well, that is the atomic packing factor for a simple cubic structure. Imagine trying to pack a square moving box with round basketballs. Because the balls are round, they just can't perfectly fill a square space, right? So in the simple cubic crystal, only 52% of the cell is actually solid matter. That means a massive 48% is literally just empty space. Crazy to think about? Okay, let's do a quick practice check to make sure we're visualizing this 3D puzzle correctly for your exam. If you have a BCC cell, so that's 8 corner atoms and 1 center atom, how many total atoms truly belong to that one specific box? Believe it or not, the answer is just 2 full atoms. Wait, why? Well, because those corner atoms are actually shared with all the other neighboring cells stacked tightly around it. You only get an eighth of each corner atom inside your specific box. So 8 times 1/8 is 1. Plus your 1 completely solid center atom, which gives us exactly 2 total atoms for a BCC structure. Makes sense, right? Up next, Section 4, Mapping with Miller indices. We've got our building blocks, but how do engineers actually map out specific slices or planes inside these structures? We use something called Miller indices. Basically, think of these as a GPS coordinate system for crystal planes. And finding them is a super simple 3-step procedure. First, you find where your flat plane slices through the X, Y, and Z axes. Second, you flip those numbers upside down, taking the reciprocal. And finally, step 3, you just clear any fractions by multiplying them out to the smallest whole numbers. Easy peasy. See how the geometric crystal plane kind of acts like a ramp intersecting our 3 axes? By using the Miller indices process, we can take those three intercept points and generate a really clean, simple set of bracketed numbers, like 111. This microscopic GPS map is absolutely crucial. Why? Because when a metal bends or snaps under pressure, it almost always fails right along these exact mathematical planes.
Time for a quick pop quiz. We have all this fantastic geometry and math, right? But how do we actually know it's true? I mean, atoms are fractions of a nanometer wide. You definitely can't just slap a crystal under a standard high school microscope and see these planes. So, how do we prove they're there?
Which brings us to Section 5, X-ray diffraction in Bragg. Historically, seeing these planes was a massive problem. But in the early 20th century, scientists like Max von Laue and the brilliant father-son team of the Braggs realized something genius. To actually see a gap as tiny as the space between atoms, we needed to use a wave that was as tiny as the atoms themselves. We needed X-rays. So, the absolute most crucial takeaway here is understanding Bragg's law. Now, your textbook is going to show you the scary-looking equation n lambda equals 2d sine theta, but let's break that down into plain English. It simply means that when X-ray waves bounce off the different layers of a crystal, they'll only perfectly sync up and shine really brightly if the angle they hit exactly matches the gap between the layers. It's honestly just like perfectly timing your pushes on a playground swing, so you go higher and higher. The parallel crystal planes essentially act as a microscopic mirror grating. When the incoming X-rays hit the atoms, they scatter. And by carefully measuring the angles of the bright spots that bounce back, engineers can literally reverse engineer the entire 3D structure of the crystal without ever physically seeing it with their own eyes. How cool is that? All right, Section 6, Final Exam Power Review. Take a deep breath. You've officially made it through the hardest material. Let's quickly lock in these key concepts so you can walk into that exam room with total confidence. Definitely keep this summary fresh in your mind. Just remember the flow of logic. The unit cell structures build the lattice. The Miller indices act as our GPS to map that lattice, and Bragg's law uses bouncing X-rays to physically prove the lattice exists. Build it, map it, prove it.
Let's test this out with a challenge problem. Let's see if we can tie the geometry and the X-ray mapping together for one final high-level engineering problem. Say you're designing a massive steel beam for a skyscraper and you have to meet super strict safety standards. You need to know exactly how far apart the microscopic fault lines in the metal are. Can we calculate that distance using what we've learned today?
Yes, we absolutely can. The spacing, which we call d, is incredibly straightforward for a cubic system. It's simply the edge length of your little room, A, divided by the square root of your Miller indices squared and added together. With this one simple formula, you can connect the physical edge of a unit cell directly to the exact GPS plane slicing right through it. So, I want you to really think about that as you walk into your exam. You aren't just memorizing abstract math or cramming random equations. You are literally learning to read the structural secrets of the entire physical world. By understanding these microscopic blueprints, you're taking the first real steps toward engineering the unbreakable materials and incredible technologies of our future. You're gonna crush this exam. Keep studying hard and stay curious.